Hello CIO world, and welcome to another study theme of chemical engineering, and this is piping system design. So in the next chapter we will go over the basics of piping system design. This includes a quick recap on how to calculate gas densities for both the real and ideal cases, as well as how to locate various kinematic viscosities from dynamic viscosities, and of course vice versa, and also calculate or locate values for constant pressure and constant volume heat capacities, as well as how to calculate vapor pressures for all components using the Harlant equation. Now, on page 7 of the study guide, you'll find information about units that are typically used in piping system design, and you should now be very much familiar with the conversion between different unit systems. In turn, you can also go to Appendix B, and you'll find some very basic conversions. It's not a lot, but these will mostly be used in the piping system design. And you can also have a look at Chapter 1 of Perry's Chemical Engineer's Handbook if you wish, for a more in-depth and detailed list which is provided there. You can of course also look online, go through sources online if you wish, if you really do need to find a unit conversion that you can't find in a textbook. Now, when we chemical engineers begin with any sorts of design, it is useful to consider general trends in the physical properties of fluids. You will learn more about this in terms of heuristics of the chemical engineering design next year. So in the final year, we go over a lot more heuristics with you. And these are, heuristics are based on extensive experience and is intended to reduce complexity and therefore the amount of calculations necessary during the initial phase of design. Now you can think about this as a general rule of thumb. Now the first heuristic that we come to is that of the density of most fluids, specifically liquids, and the density of liquids typically range from about 800 Sg to 1000 SG, or in other words 800 kilogram per meter cube and 1000 kilogram per meter cube. Okay, obviously there are a few exceptions. So some fluids can have much less, like methane liquid in its liquid form. Look at the temperature, 165 degrees Celsius, as well as things like sulfuric acid, which can be quite high if it's very concentrated. Just recall what Sg is. Sg is the ratio of a density. So for example, for methane it is 465 divided by the reference density for water at 4 degrees Celsius, which we round off to 1000 kilogram per meter cube. So in other words, the Sg of methane in this case will be 0.465. For acetic acid it will be 1.049, etc. So note the examples that are shown here. Now, what about gases? Firstly, for the ideal case, we may assume the ideal gas law holds. Note how we obtain the density from this law, as we will make use of this quite often when dealing with gases. If you require greater accuracy, we may consider the use of compressibility factors, which is Z, which are estimated using an equation of state for real gases, such as the Peng-Robinson equation, as well as the Redlich-Kwong equation. These two equations are considered the most general or widely used. But obviously, if you use software like Aspen Tech, they offer you a whole array of packages for the equations of state on how to calculate vapor, liquid equilibria, etc. And you'll learn a little bit more about that next semester, I think. Or the second semester. But either way, next year you will also be using a lot of these. There are also plots for compressibility factors that are available to you in the literature. Perry's, for example, has some tables that are present in Chapter 2 and covers the most important fluids. Keep in mind, however, that compressibility factors work to adjust the property you are trying to predict. So for gases that tend towards low pressures also tend towards ideality. So they tend towards becoming an ideal gas. So we can use the ideal gas law to predict volumes and pressures, etc. Whereas at moderate pressures, intermolecular forces start taking hold, and these tend to be attractive forces, and so the volume tends to decrease more than what is expected. And in the case of high pressures where gases are really colliding into each other, more and more repulsive forces take hold, and these keep the volume higher than what is actually typically expected. For viscosity, it is something you have now seen quite a bit of lately, especially in this year. Typical values used for dynamic viscosity are in centipoise or poise, as well as Pascal second or kilogram per meter second. And this uses the symbol mu for its representation. It's related to the kinematic viscosity by rho, the density, which is the density of the fluid in question. Kinematic viscosity has units of centistokes or stokes or meter squared per second, and uses the alternative symbol of nu, which looks like a V. Just remember that this is a Greek symbol. Also take note of how temperature and pressure influences viscosities, where liquid viscosities tend to decrease with increasing temperature and decreasing pressure, while gaseous viscosities tend to increase with increasing temperature, but tend to be independent of pressure at low enough pressures. Obviously, when we get to higher pressures, we start talking about supercritical fluids, and then pressure starts to play a role for gases. In this module, we will typically be required to learn a few more parameters for explaining certain physical properties and thermodynamic properties in the design of piping systems. So we will require a new parameter, which we will refer to here as the specific heat ratio, which is given the symbol of K, which is the ratio of specific heats at constant pressure and constant volume, respectively. We will use these in later calculations. Data for the heat capacities of gases are often taking the form of polynomials, where the constants can easily be found online, such as if you go to the government website of the United States called NIST, which is the NIST library. They have a lot of physical chemi-physical data. You can also find these constants in handbooks such as Perry's, of course. Now, equations for vapor pressures are also available, and the most widely used of them is the Anton equation. And of course, we can find the A and B constants also in the literature. This concludes the second chapter for the Piping System Handbook. And now we will continue into chapter 3, which deals with the basics of the dynamics of pipe flow. In this chapter, we will define what is meant by fluid dynamics, distinguish between ideal and real fluids, and get introduced to the 3 fundamental equations that will be used to describe fluid flow for the rest of this semester. We will also be introduced to the mechanical energy balance, which you should recognize and learn how to apply this equation to a process design. We will also have a look at flow regimes and how these affect fluid flow, and also recall our understanding of the boundary layer concept very briefly. There are also 2 principal equations that we will consider in this chapter, which are used to describe the effect of frictional losses in flowing fluids inside pipes, and learn how to calculate friction factors to account for such losses. We should also be aware of the correlation factor that is associated with calculating the kinetic energy losses through pipelines, but we also look at this in further details in chapter 4. Also understand how we came to express surface roughness based on the work by Nikaradze, who used sand grains in order to calculate a roughness scale. So, to begin, let's first look at differences of hydrodynamics and hydraulics. Now, hydrodynamics is a science that is typically based on describing fluid motions using imaginary particles or systems, the results of which have some application but very little practical value to us as engineers. Hydraulics, on the other hand, is a very specific form of hydrodynamics that deals with liquids only. However, using the understanding that is developed in these two fields of study, we obtain through rigorous experimentation and experience empirical equations that more accurately describe what we see or what we expect to see in practice. It is these equations which we'll now be introduced to. We should be aware of certain simplifications that sometimes, but not usually, are made when considering real fluids. Usually when working with ideal fluids, we neglect the effects of viscosity and assume frictional losses to be minimal. But for real fluids, especially those running through the very, very long piping systems or pipelines that we will be familiar with as engineers, friction becomes more significant and must or should be accounted for when determining energy losses for the fluid in question, and you will learn why this is important shortly. In our analysis of fluid flows, we will adopt what is referred to as the mechanical energy balance. And a derivation of this equation is provided in the handbook for your perusal. We're not going to go over it in class. I think you've had enough of that last semester. But be sure to go through this yourselves and understand the derivation. You'll recognize that it is similar to the energy conservation law, the intercorrelation approach, which we were familiar with. This is obviously just looking at differences from 2 points, or how many ever points you want to look at. The mechanical energy balance accounts for all types of energy differences one would come across in practice, and can be expressed in 2 different ways, which we will use interchangeably through the semester. The first is the more general way, where energy is expressed in joules per meter cube, while the second way is often used and typically expressed as a difference in meter head, which is specific to the fluid in question. We will learn why this form is most useful to us, and it has to do with pumps and visualizing pressure in terms of elevations. Now, the first term of the mechanical energy balance refers to differences in pressure at the endpoints at the process. So, for example, tank 1 and tank 2 may be at different pressures from each other, or one or both of them may be exposed to atmospheric pressure, for instance. The second term of our equation relates to the difference in elevation of the fluid. Alright, so pay attention where the 2 heights of the fluids at the different endpoints is being measured. Don't let this confuse you. The third term is made up of differences in the kinetic energy of the fluid between the 2 points that are or that we are referencing in the process. The fourth term is going to be the one that is the most difficult to calculate, and it accounts for losses in energy of the system due to friction. Here I have zoomed into a part of the pipeline and shown the interactions that the fluid would have on its confines. So how does the fluid react to the wall that is confining it to its space? And really it's this that results in the losses in energy due to friction of pipelines. And the very last term on the right-hand side of our equation is the energy that is provided or taken by a fluid mover or consumer, such as a compressor or a pump or a turbine, etc. Okay, so the first 3 terms of our equation are representing things like static pressure energy, potential energy, and kinetic energy, and are really simple enough to determine. These are just straight values, this minus this, etc. While the fourth term represents all the losses in energy that relates to frictional losses, right, and requires much more rigorous effort for its determination. The second most important equation to use when designing piping systems is, of course, the Reynolds number, which we know to be a dimensionless number. Here, x is some linear dimension that is specific to the flow, so it can be flow over the bonnet of a car or flow over a weir, but in this case, for piping systems, this x refers to the diameter through which the fluid has to flow. You will often see the concept of fully developed flow. This is often mentioned, and this has to do with the development of the fluid profile inside a pipe. When a fluid is flowing, as it enters a pipe, the velocity profile is not yet steady. Only at some point downstream will the profile be developed, and the length of pipe it takes to achieve this fully developed flow is then given by the correlation of L equal to 0.058 times by the Reynolds number times by the diameter D. And this is specific for turbulent flow. There are similar correlations for laminar flow, which we will also discuss in heat transfer. The occurrence of laminar, transition, and turbulent flows is specific to the geometry of the surface that interacts with the fluid in question. So for pipes, the laminar flow is typically achieved below Reynolds numbers of 2000, and for Reynolds numbers between 2000 and 4000, we say that the flow is transitional between laminar and turbulent, while flow above 4000 is said to be completely turbulent. Note, however, that there may often be exceptions to the rule, but these actually are more exceptions than the rule itself. So you can typically just take these ranges that are shown here and assume them, safely for most applications. Now, we were introduced to the Harlant equation when dealing with the hydrodynamics during the transfer processes module. The Harlant equation is, however, only applicable to laminar flow, while the Darcy-Weisbach equation is actually the preferred equation to use, since we can easily account for frictional losses using some empirical equation, and we can apply this equation to laminar and as well as turbulent flows. Right, so we calculate the friction factor as F prime, which is shown here by the apostrophe F. Also recall how we describe the velocity profile. We've seen this before, and this is typical for laminar flows. However, where turbulent flows tend to be more blunt, obviously this equation does no longer really describe this profile, with the profile being more closer to the fluid wall interface than going through the entire section of flow. We typically take the average velocity to equal half of the maximum velocity at the determined flow rate. So this maximum is usually determined at the center of inside a pipeline. The relation that we've just shown here, together with the correction factor that is used for kinetic energy terms in the MEBs that we will be using, is important, and a student should really make sure to read the discussions on this in the handbook. I know that there's also a TUT question that uses this correlation as well as the alpha EK. So just have a look at that tutorial. Now, let us focus a bit more on the equations which describe these frictional losses in the pipe. I think you would have come across the particular one shown here for laminar flow. So the friction factor is often used with the Darcy-Weisbach equation, and in this case we would then calculate this friction factor F prime as a ratio between the value of 64 and the Reynolds number for the fluid flowing through a pipe. For different flow regimes, we have a few more options to calculate the friction factor, and these depend not only on the type of regime, but also on the type of pipe being used. So for smooth pipes, those that are less rough, at turbulent flows, the Prandtl equation is typically used. When flow is fully rough and turbulent, the von Karman equation is also preferred, while we could make use of the Colebrook equation, which is applicable for all flow regimes, as well as for all smooth, transitional, and fully rough pipes. And also pay attention, there's another correlation as well called the Harlant equation, which we can also use. Bear in mind that regardless of which equation you use, the Harlant or the Colebrook or the Churchill equations, which we'll also learn in Chapter 4, you should more or less get the same friction factor. It doesn't really change by much. So it's not going to affect your final answers at the end. All right. So this marks the end of our discussion on the basics of dynamics of pipe flow. Next up, we will take a look at how we apply this knowledge in piping systems. The first three terms that we were introduced to in the mechanical energy balance are quite trivial in their determination, and often for turbulent flows, the kinetic energy term is dwarfed by the other terms, such that we will typically take this effect to be negligible. The fourth term, the friction factor or the frictional losses term, comprises various aspects of flow, not just for friction due to the pipe fittings and valves, okay, but also the loss due to equipment in the process, as well as the control valves. Now, control valves are specifically used to manage energy and flow for the process, and we will go into more detail about the design of control valves at a later stage in time. Right. As with any sort of balance, what we typically do, we can apply the mechanical energy balance between two specific points in a process, as shown here. These points are known as terminal points. The endpoints of our system are typically fixed and would be independent of flow. So it doesn't matter what the flow is at point 3, the pressures inside tank 1 and tank 2 will more or less stay the same. And so these are going to be non-variable pressure points. The mechanical energy balance taken between these two terminal points would contain obviously all the terms in the mechanical energy balance, and such a balance would be used for the determination of energy required by a fluid mover to obtain the desired flow. So we would want to know all the frictional losses across this pipe, etc. What is the kinetic energy differences, elevation, endpoint differences, and using this information, we would then specify a pump and say this pump should be used in this particular application. All right. Now, if you consider the mechanical energy balance, you would, certain terms would change with certain flow rates, while others will remain unchanged. So, like the endpoint differences, the elevation would also not necessarily change at all with changes to fluid flow, while the kinetic energy and the frictional losses would be affected by the flow. So when there's no flow, there's no frictional losses. When there's no flow, there's no kinetic energy losses. And therefore, the kinetic energy and the frictional losses terms are collectively referred to as the total varying pressure, or the TVP differences. This will become very important later on in our piping system design chapters, so please be sure to remember this. Also remember that the frictional losses term is made up of various aspects of frictional losses that can take place in the form of equipment, control valves, etc. Now, in the design of control valves, we consider the total varying pressures, but we also then consider what is known as the subtotal varying pressures first, since a control valve needs to control these terms. So of course, a control valve has no effect on endpoint and potential differences of our pressures. So again, keep this in the back of your mind for later application. Now, in the design of piping systems, we often work with different units, and depending on what we want to determine, sometimes we work with mass flow rates, other times we will be interested in volumetric flow rates. So the handbook provides a nice, neat summary of the Darcy-Weisbach equation that has been converted for using different units of interest, as well as Reynolds number. So pay special attention to the units that you are using. Make sure that Reynolds number turns out to be unitless, and make sure that pressures and diameters are all in the correct units. It is often here where calculations do tend to go awry. Let's stop for a minute here and do some practical exercises. See if you can determine the frictional factors, or the friction factors, for the following exercises using the Moody chart, which is at the back of the handbook. It is very important to practice these types of questions, as they are often going to take you a lot of time, and you can make a lot of careless mistakes when completing them. So it helps to make sure that you get enough practice in, so that your time isn't spent just trying to figure out this information. So quickly take a pause here and try out the following. And once you have tried those out, use the equations in the textbook that applies, and see if you can also get the following frictional factors, or friction factors. Typically, friction factors that we will expect are f prime equal to 0.018 to 0.020. And this is very useful because oftentimes in our initial calculations, we aren't able to determine a friction factor yet. And so we kind of have to guess first and then do a recalculation once we have some values to calculate f prime. Fortunately, f prime does converge quite quickly, so we only have to do 1 or 2 iterations at a time. So in the previous exercise, it was shown that the friction factors can be determined for straight pipes using various means, and it is really up to you to decide which options you want to make use of, or which options are available for use. Design is often open-ended, and there aren't always guidelines to help you in these sorts of decisions. If you consider the Darcy-Weisbach equation, what we have in essence is we have to determine the f prime term. Okay, so this is what we have now kind of been having a look at. Next, we will consider how do we account for frictional losses that can be caused by things like restrictions. Okay, so in the previous exercise, we specifically looked at f prime due to the pipe itself. So how does the pipe contribute to frictional loss? Now we want to have a look at how do fittings, so different types of restrictions, fittings and bends and let's say valves, hand valves, butterfly valves. How do all of these resistances add to frictional losses? And how we do this is by adding a theoretical amount or an imaginary amount of pipe length to this equation. But remember, this is only an imaginary length, and it is not a real length of the pipeline in question. Here again, there are two options which we can choose from. So the first option we refer to as the LR over D method. So this is the length of the resistor divided by a diameter. The LR over D value is specific to the type of fitting or equation, and an equivalent length of pipe is determined for this fitting by multiplying the LR over D value by the diameter being used for this specific pipeline. The resulting equivalent length of the restrictions, or the sum of all of these, is then added to the actual length of the pipeline, LP, and this new length is then used in the determination of a pressure drop due to the combined effects of the pipe length and the presence of the restrictions. The second option at our disposal is the resistance coefficient method. This coefficient is in fact equivalent to the friction factor F prime multiplied by the L R over D for a specific type of resistance. This resistance coefficient is often used in conjunction with the other equivalent length method that I've just discussed now. So we can therefore put these two terms into our equations that we are working with, the Darcy-Weisbach equation, in the following format, right? And it looks something like this, and then obviously we can simplify it to this. In other words, we have in the yellow the LR over D, and in the orange we have the resistance K divided by F prime. We multiply this by F prime and obviously the diameter, which I've left out here, oopsie, but I'll get onto this now. So just some restrictions that we must keep in mind. Just keep in mind that there are limits that apply to making use of these correlations, and also, if you are deep within the realms of laminar flow, you may need to just adjust these correlations simply, and well, the adjustments may be slight or may be quite vigorous, and therefore there's more information on how to do this on page 34, so do be sure to go over this in your own time. Now, for even more accuracy, you may consider making use of the 2K method as well, which is discussed in more detail on page 31 as well. You determine two specific K coefficients, one at a Reynolds number of 1 and the other at a Reynolds number that approaches infinity. Let us now consider another exercise. So in this exercise, make use of the following information and determine the equivalent length by calculating the resistant lengths LR for these resistances. The answers are going to be provided for you, and the final answer that you should get in this case is equal to 72.5 meter. See if you can quickly determine these yourself. First off, we find the LR over D values and the resistance coefficients that may apply. We multiply these by the number of components per resistance and then sum up the LR over D values and the K values as shown. We next divide the sum of the resistance coefficients K by the friction factor F prime and add this to the sum of the LR over D values. We then multiply the sum by the diameter and make sure that you correct for the unit difference here. Oftentimes we use a millimeter for diameters, so just remember your units and make sure that you calculate meters instead. And what you should obtain is LR equal to 22.5 meter. You add this to LP, which is 50 meter, in order to get the total length of resistance that causes the pressure drop. And this is 72.5 meter. Okay. And so here I show the addition. Okay, so add this resistance length to the pipe length, obtain an equivalent theoretical length, so you can determine the total pressure drop for this process due to the pipe as well as all the fittings. If you're still unsure about these calculations, also read up about these on page 31 of the handbook, or phone a friend, or just ask me. If we have some pipelines where the diameters change, we typically talk about reducers or enlargers, or maybe you have just two different pipelines entering and leaving a process. We can still calculate the pressure drop across this or these sets of pipelines by adding additional terminal points or splitting up our calculations and then summing up all the calculations in the mechanical energy balance. All right, because the mechanical energy balance is just an energy balance, and so the energy balances are summated. This energy plus this energy plus this energy is equal to the total. Okay, so just remember to include any of the resistors or enlargers that may be present in the calculation. So in some cases, it might be preferable instead to prorate. Now, prorating is used to combine the different diameters as follows. So consider two pipelines of diameter dA and diameter dB. The total pressure drop across the pipes is the sum of the individual pressure drops across each section. We can substitute into each term the Darcy-Weisbach equation and then simplify the equation as shown, where P nu A and P nu B are the dynamic pressures for each of the pipe section A and B. Now, since P nu is directly proportional to 1 over D to the power of 4, we prorate P nu as follows, and can substitute this result into our previous equation that defines the total pressure drop for the system. Let us now consider another example where we have to determine how flow splits through a T. We will go over this in class, so I'll go over the calculations with you just to clarify things, but try to attempt this yourself and see whether you understand how to do this or not. It is a fun exercise. Discuss it amongst yourselves as well and see if you can come up with a reasonable solution. And in this case, the idea here is that you're not given all the information required to begin with. There's a lot of unknowns and we need to make guesstimates initially. This is by far the most frustrating part of the problem solving. And we need to really become more used to not knowing a lot of the information. So the initial answers can be obtained from using estimates as follows. And once you can make a better determination of f prime, we can then do the calculations again. And only then should you be able to include all the resistances, take all of these into account, and make a better determination of how the flow splits. And then you should be able to obtain the following values, more or less. Don't try to get the exact values though, that's not the point. The point is to practice the exercise, how to go about doing this. Okay, so we're going to discuss this in class at a later stage. Another exercise you can try yourselves is making use of the various appendices to calculate resistance coefficients K for reducers and enlargers. If you turn to Appendix C4 and look at the right-hand page, you will see a chart that can be used to determine the Kr value, which is on the y-axis, by first calculating the ratio of dA to dB, find this ratio on the x-axis, and then locate the point that corresponds to this point on the line, which corresponds to one of 4 scenarios. So note that there are 4 lines here. The lines correspond to the softer type reducers and enlargers, and the other 2 lines correspond to sudden or harder type or more abrupt enlargers and reducers. Okay, so once you have found the correct point on the correct curve, you can then read off on the y-axis a Kr value. So see if you can determine this yourself for the following examples. And of course, here I've provided you with the answers already to kind of help you along your way. Okay. Often with older literature, one would come across pressure drops given on a per meter basis of length of pipe. Okay, so it will be per 1 meter length of pipe. The idea here is to then multiply this value by the actual length of pipe that is applicable to your process. We will soon use this as well to complete other piping system design calculations in later chapters. So just remember this definition for now. For any design that you do, you must take into account those things which you cannot account for. So remember, any equation you make use of is prone to certain inaccuracies. And so to use these calculations in practice or to apply them to a real situation, it is very good practice to factor in a safety factor. Okay, so therefore, whatever you have calculated as a pressure loss across a system, just add to this 20%, so adjust by 20% increase, just to be on the safe side, so that when the system works slightly better than you had anticipated, your boss will pat you on the back and say, "Good job, it works." Right, so equipment usually has a specific pressure drop that applies at a specific flow rate. So let's say this filter operates at a flow rate of 1 kilogram per second. As with other pressure drops that we have discussed already, pressure drops at other flow rates can be prorated for by squaring the ratio of the new flow rate that is of interest and the reference flow rate. So to determine the pressure drop due to elevation, we use the typical static head equation, which is rho GH, where we use Z in place of H as shown. And for the kinetic energy term, we assume a correlation factor of alpha equal 2 for laminar flow, and we take alpha equal to 1 for all other flow regimes. It should, however, be noted, as I've said before, however, that since kinetic energy drops through pipelines are so small compared to other terms, we generally assume this effect to be negligible within pipelines. However, just remember that when you have flow that is arresting itself as it reaches a vessel, then we can do these sorts of kinetic energy calculations. Okay, and with this, we have completed the first 4 chapters of piping systems design already. So well done, and be sure to complete the rest of the tutorials that you are able to complete. You'll find that those that you are not able to complete yet, we will get to in a short while. But for now, practice, practice, practice. Piping system design is not easy, and especially if you have not been practicing. Good luck and goodbye for now.